Good evening. My name is Tony Beasley. I'm the Director of the National Radio Astronomy Observatory, and welcome to the 47th Annual Jansky Lecture. The name Carl Jansky is quite a famous name in science. He was the first person to detect radio emission from the universe. He did that as a Bell Lab engineer in 1932, investigating issues with transatlantic radio phone calls. Through his efforts and his insights, we now have the field of radio astronomy. He opened a new window onto our universe, and today we have a US National Radio Astronomy Observatory that's made up of some very important instruments. We have the Carl Jansky Very Large Array in New Mexico. We have the Robert C. Byrd Green Bank Telescope in West Virginia. We have the Very Long Baseline Array we'll hear a lot about tonight, distributed across the US. And finally, we're partners in the Atacama Large Millimeter Array in Chile. And so directly and indirectly, all of those instruments arose from the research and the work that Carl Jansky did. That field of radio astronomy has resulted in thousands of important scientific results, in a handful of Nobel Prizes, and there are today employed throughout the world thousands, tens of thousands of scientists, engineers, administrators, and other types working in this field. And NRAO is very proud to acknowledge and honour Carl's achievements with this distinguished lecture series. I'm very pleased to welcome Carl's son David Jansky to the lecture hall here tonight, so welcome. The lecture tonight will be given by Dr. Mark Reid of the Harvard-Smithsonian Center for Astrophysics. The title of his talk is Measuring the Cosmos. Mark finished his PhD at Caltech in 1975, studying radio imaging studies of the envelopes of variable stars. He moved to the Harvard-Smithsonian Center for Astrophysics in 1975. In 1977 to 79, he was actually a member of the NRAO scientific staff, but he left under a cloud we can't really tell. His records have been sealed for 50 years. He returned to the CFA as a radio astronomer. And since that time, he's been a senior radio astronomer. He's been the division associate director there and the director of the CFA Radio Telescope Data Center. So this is a long and very illustrious career. Mark's had numerous scientific and technical accomplishments. He is an acknowledged expert in the use of high-resolution radio interferometry to explore the physics of cosmic mazes. He is widely recognized as the pioneer of ultra-high precision very long baseline interferometry astrometry, a science that measures the astronomical positions, motions, and distances of objects with extraordinary accuracy and precision. Currently, he's the lead on two very important teams. He's the lead on an international team in a major 5-year project with the VLBA to accurately determine the spiral structure and kinematics of the Milky Way, some of which we might hear about tonight, and also on a team making the first direct measurements of the proper motions of nearby galaxies in our universe. Over the years, Mark has received several awards, the Alexander von Humboldt Senior Research Award in 1999, the AAS Beatrice Tinsley Prize for Outstanding Career Contributions a few years ago, and the Smithsonian Research Prize in 2011. I have two personal comments to make here. Mark and I have been friends for 20 years, and we've played a lot of golf together. And in fact, he challenged me to play today. Every time we've played, he's beaten me so badly that I'm forced to conclude that he is actually a cheat. And so, despite the fact that he is one of the country's leading astronomers and really a lovely guy, don't play golf with him for money. The second point I would make is that I personally have spent my career building and operating telescopes of one type or another. And I actually came to NRAO originally to help build the VLBA. And when you work at an observatory, really the deal that you make with the scientific community is that we build the best instruments and you do outstanding science with them. And so I think that over the years, the deal between the VLBA and Mark has been well met, and the VLBA is the best instrument of its type on this planet, and there is no one better than Mark and his team using it today. So on behalf of the observatory, I'd like to present him this plaque as a token of our appreciation.
Okay, can you hear me back there? Great, okay. So I think Tony let me off a little easy here. I was a little worried about what he was going to say. All of it was not true. Okay. Yeah, we can go down. So the title of my talk is kind of a gaudy title, Measuring the Cosmos, but you'll see in a while why I called it that. Can we dim that? Go down to the bottom one, yeah. So if you look at this image of the sky, this is a very modern image of the sky, a very small piece of the sky taken by the Hubble Space Telescope, staring for a long time at this. And if you then ask yourself, for example, in the time when Carl Jansky was in college, which is not all that long ago, in fact, there are probably people in this room who might have been alive at that point. If you went to astronomers at any prestigious institution or anywhere else and asked them, what are these things like this and this and this? Or ask them which ones are nearby and which ones are far away. Or you could ask them, how far away are any of these objects on this image? They would have no answer for any of those questions. Because these are galaxies. They were called spiral nebula and other nebula at that point. But people didn't know if they were inside the Milky Way near to us and that was the whole universe, or if these things were very distant. And the reason is that measuring distance in astronomy is really very hard. Things are very far away, and the sky is essentially flat. So it's very hard to tell what's nearby and what is far. And so what this talk is going to recount the history of measuring distance in astronomy, which is really a fascinating story. And toward the end, I'll talk a bit about how we are doing it today. So let's go back much further in time than the 1920s, when I said the astronomers of that time would not know anything about this image. Let's go back about a little over 2,000 years. There we go, get that working. Okay, here in about 200 BC is a picture of Hipparchus. And he was the first one who really did an excellent astronomical measurement of distance. He measured the distance to the moon, and he did this basically with 2 bits of information. He noted there was a total eclipse of the sun. It was a total eclipse in Hellespont in Turkey there, on the northern side of the Mediterranean. And it was noted to be an 80% eclipse in Alexandria, in modern-day Egypt. And he probably made a drawing in the sand, because there was no paper at this point, no pens. And he probably made a drawing something like this. So we have the Earth on the left, the moon over here intercepting the light from the sun. And up here labeled H is Hellespont in Turkey, where the eclipse was total. And so that means that if you look at a ray starting at the sun, coming back, hits the limb of the moon and comes to the observer, and a ray from the southern side of the sun here coming back also hits the limb of the moon and comes to the observer. So you get a total eclipse. The moon blocks all the light. But in Alexandria, labeled A here, you follow those green lines, and it misses the sun up here and covers about 80% of the sun. The moon covers about 80% here, leaving about 20% of the sun exposed. So he drew this diagram, and you have a triangle from H to A to the limb of the moon here. And I've reproduced that triangle down here. Now he knew the distance from Hellespont to Alexandria, and he knew this angle, this small angle here, because it was 20% of the angular size of the sun. The sun is about a ½ degree across, so that angle was 1/10 of 1 degree. He had to make a little correction for a projection of this distance here, which was not hard to do. And based on that, he could calculate the distance to the moon. The distance d is given by this projected distance divided by this angle. You have to convert to radians for that. And so he basically did this calculation and presumably got a distance of about 400,000 kilometers, which is really pretty close to the modern day value for the distance to the moon. Really quite an ingenious method. The moon is very close, of course, and that allows you to do this from the Earth. And in fact, about 2,000 years after Hipparchus did this, a French astronomer named Nicolas Louis de la Caille sort of retried Hipparchus's observations, but all the way across the Earth. So he used observations at the southern tip of Africa and observations in Europe. And he basically would see something like this. The moon blinked here would be, say, here in Europe and here in South Africa against background stars. So you can actually see you get a different position, and you can measure the angle. The problem was what to do next. Planets are too far away to measure distance in this technique from the Earth, and certainly the stars proved to be far too far away for this. And so at this point in time, astronomers had no way to answer the question, how big is the universe, which to them at that point meant how far away are the stars. There was also another great unanswered question, and that was whether or not the sun went around the Earth or the Earth went around the sun. And indeed, most scientists of the time, from Hipparchus all the way up into the 1600s at least, thought that the geocentric cosmology explained things, that the Earth was at the center of the universe, the sun and everything else went around. And so even Hipparchus, who measured the distance to the moon, believed in a geocentric cosmology. But it's interesting that even before Hipparchus, Aristarchus of Samos in about 250 BC forwarded a theory that the sun was at the center and the Earth went around the sun. And it wasn't really until about the 1500s when Nicholas Copernicus compiled enough data that would convince most people that the Earth went around the sun. So what was really needed, even up to the 1500s and beyond, was a clear test of which system was right. And the clear test that came up was measuring what's called annual parallax or trigonometric parallax. And that is, if you have the sun here and the Earth if the Earth went around the sun and you viewed a nearby star against a background of distant stars, it should appear to move relative to them. So if you're here in December, when the Earth is on this side of the sun, you follow this ray toward this star, and you should see it between this star and this star, this cyan and this purple star. It should appear roughly like this on the sky, much like that picture of the moon I showed earlier. You wait 6 months, the Earth has come around here. You're viewing from quite a different vantage point now, twice the distance of the Earth to the sun. You follow this ray, and this star, nearby star, should appear between these objects, these stars. And the constellation should appear like that. And so if you could measure this angle P for parallax, you could calculate the distance to the star in exactly the same way that Hipparchus calculated the distance to the moon. It turns out that these angles happen to be quite small because stars are far away. For the nearest stars, as you'll see later in the talk, this angle P is about an arc second or smaller. That means, by the way, if you take this angle in arc seconds and invert it, 1 over this angle, you get a distance in what is called parsecs, which is a good astronomical term for distance. And a parsec is about 3 light years, and it's also about the distance to the nearest star. Just for comparison, the center of the Milky Way, which certainly wasn't understood back then, has a parallax of about 1/10,000th of a second of arc. So I'll be telling you later about measuring angles like that. Well, because there were 2 huge scientific questions that could be answered by measuring a stellar parallax, the first being how big is the universe, and the second, whether the geocentric or heliocentric cosmology explained things, there was literally a race to measure the cosmos. And by the way, that's a title of a really excellent book, if you like this subject, by Alan Hirschfeld in 2001, Parallax, the Race to Measure the Cosmos. And we'll start here with Tycho Brahe in about 1570. He made some interesting astronomical discoveries. He discovered a new star, which was a supernova, in one of the spiral arms of the Milky Way. And he built really big quadrant instruments, which are naked eye instruments, but allowed you to measure angles. And he tried to measure stellar parallax, but there is no way you can measure parallax with that sort of an instrument. You really need a telescope. And so telescopes date basically from the time of Galileo in about 1610. He built the first astronomical telescope almost exactly 400 years ago. And he discovered lots of things, that the moon was not a perfect sphere but had mountains on it, that the planet Jupiter had 4 satellites, which are now named Galilean satellites after Galileo Galilei. He discovered the rings around Saturn, and that Venus, the planet closest to us, interior from the Earth, had phases, just as the moon did. Now, all of these things put together certainly suggested that the Earth was not at the center of the universe, and that the universe was perfect with crystalline spheres and things like that. And so that did favor a heliocentric cosmology, but certainly without a critical test like stellar parallax, no one believed that, or very few people did. He made one really interesting suggestion for measuring parallax of stars, and that is, he said, don't try to measure the absolute position of a star, as I sort of diagrammed earlier. Come back 6 months later and measure its absolute position again. Measure a differential position between stars, because you can make differential measurements much more accurately than absolute ones. And that's basically what everybody does these days. And so that will come back throughout the talk. But it was an amazingly scientific approach that he forwarded. Okay, now we go to Robert Hooke. And he was quite an eccentric and quite an interesting fellow. Sort of did everything in science. He invented the microscope, a very famous noted biologist from that. He discovered Hooke's law for springs. He was quite a good physicist. He was an astronomer, as I'll show you and tell you. He was the surveyor of London, and he was basically the first president of the Royal Society in London. So he did everything. Now, he tried to measure parallax, and he recognized one thing, the first most important thing, and that's that light is refracted through the Earth's atmosphere. And that bends the light and makes it appear to come from a different position. And if you're going to try to measure positions very accurately, you better know about refraction. And I put this picture of the sun up here setting over the ocean. And when one sees the sun like that, it actually has totally set. It is really totally behind the limb of the Earth. But the light is bent through the Earth's atmosphere, and it appears to be about 1/2 degree above the horizon. So that's a huge effect, about 1/2 degree effect if you look horizontally through the Earth's atmosphere. And so he thought, well, I'll try to minimize that effect by looking vertically, where refraction really is not very important. And so he picked a star that went vertically overhead in London, and he built a telescope that went from the basement through the roof of his mother's house. He hung a plumb bob next to it, and he would then see when the star transited and came through the telescope, how the telescope was tipped with respect to the plumb bob. So he could measure an angle, basically trying to measure an absolute parallax. And so this source, the star he was looking at is called Gamma Draconis up here. And he made some measurements. He detected it at night in July of 1669. And he went back in October in daylight, basically, and was able to find the star. And he did measure a position shift. Probably it was about 10 arc seconds or so, seconds of arc. But he fell ill before he could conclude these observations and died a couple of years later, so he was unable to do it. Now I realized I was going to tell you what an arc second was because I forgot to do that. Let me start that. An arc second is a pretty small angle. Basically, if you take a circle, you can divide it into 360 degrees. You can divide each degree into 60 arc minutes, and you can take each arc minute and divide it into 60, and you get arc seconds. It's basically like time, but we only have 24 hours in a day, and and 360 degrees in a circle. So 1 arc second is the angle going around a circle, what 1 second of time is to about 2 weeks total. So it's a very small angle. The human eye can see about 40 arc second resolution. That is, you can resolve 2 stars maybe that are about 40 arc seconds apart. So it's 1 arc second is way beyond what the human eye can do. Okay. Yes. Isaac, okay. So he gave up on this and then later died, as I said. And there is no modern portrait, no portrait of Robert Hooke that survives to today. This is a modern portrait made a few years ago based on descriptions of Robert Hooke. Now, there almost surely was a portrait because all of the Royal Society presidents had their portraits. But the next president of the Royal Society was Isaac Newton. And Isaac Newton and Robert Hooke did not get along. Robert Hooke claimed to have discovered the inverse square law for gravity. And Isaac Newton probably rightly said he had provided the firm evidence for that. And the Royal Society moved offices in about 1710, and at that point, Robert Hooke's portrait never appeared again. And it's surmised that Newton conveniently lost it. So let's move on to James Bradley in about 1750 now, in London again, and he tried Hooke's experiment again, but with a much better telescope. And he was able to get much higher accuracy. So he looked at this star going vertically overhead in London, Gamma Draconis. And he was looking for an effect like this. He was looking for a shift in position, in this case declination or north-south position, of about, well, he didn't know the amplitude of the effect. It could have been a few arc seconds. I've drawn this as a 20 arc second shift. And he said thought it should be furthest south in December here in 1725. And then if he were to come back, say 6 months later in June of 1726, he expected it to be further north by 20 arc seconds with respect to the average here. So he expected to see this what's called sinusoidal shift of position as a function of time, but he didn't know the amplitude of that effect. That would be the parallax, which would give you the distance, and he didn't know the distance. Here's what he got. He got sort of a sinusoidal effect in blue here, but it peaked at the wrong time. It peaked in about March of the year. Well, this really startled him. He tried measuring another star and got the same effect. He thought maybe there was something wrong with his telescope, so he rebuilt the telescope and he got the same effect. And for quite a while, he could not understand what was going on. And the story goes that he was sailing. And he looked up at the flag at the top of the mast, which can indicate the direction of the wind. And when the sailboat tacked, he expected that the flag at the top would respond to the direction of the wind at all times. And so if the wind is coming down from the top here, this flag would have come down in this direction. And after the sailboat tacked, he expected it also to point down. But he found it pointed in a different direction every time the boat tacked. And he said, well, I doubt the wind changed every time the boat tacked to fool me. And so somehow the direction and speed of the boat had something to do with the apparent direction of the wind. And so from that he surmised, well, what if the motion of the Earth and direction of motion of the Earth affects how light comes to it and shifts the apparent position of light, which is indeed what happens. It's called aberration of light. The effect is about 20 arc seconds over the year, and so that explains this curve. Now, he wasn't able to measure a parallax, but he did discover this. And here is roughly the effect he would have gotten on the star Gamma Draconis by this dashed line. That's the parallax, which I don't think you can see from there, because the parallax is about 2/100ths of 1 arc second instead of 20 arc seconds. So it's about 10,000 times smaller than this sine wave. So that's what he was going for, but he didn't know how far away this star was. He did put a limit. He said it's the parallax, or that angle, is less than about half an arc second, which meant the star was more than about 2 parsecs or 6 light years from the sun. But he had no chance of measuring the 2/100th parallax, arc second parallax on this. It's interesting, this confirmed actually that the Earth went around the sun rather than the Earth being stationary and the sun going around the Earth, because to have aberration of light, you have to have a moving source, a reference frame. And so basically that did confirm that the Earth went around the sun. Well, our story now shifts to William Herschel. He was actually German. He emigrated to England, and he was quite an accomplished both scientist and musician. He composed a lot of very good music, and he was an excellent astronomer. He made very large reflecting telescopes, and he wanted to measure stellar parallax, and he was looking for pairs of stars that were close together on the sky, what Galileo suggested as the best method for doing this. He wanted a nearby star that perhaps was bright, and a distant star that was dim, very close together, and measure the change in relative position between the two. So he was scanning the sky for double stars, as they're called, and bumped into the planet Uranus. And of course, that made him instantly quite famous, finding a new planet. And it's interesting, he cataloged lots of these double stars. An English naturalist named John Mitchell looked at this and did what I consider an amazingly modern analysis. He said, given the distribution of numbers of stars on the sky, what are the odds by chance 2 stars would be that close together? And you can quantify that. And he found that the odds were very, very low, that this many pairs of stars could by chance be that close together. And so basically, that showed that these stars had to be related to each other. They had to be bound to each other gravitationally. And they're basically, astronomers call them binaries. And that actually proved that not all stars were the same brightness, which was not known at that time. Because you'd had 2 stars, a dim one and a bright one, that were bound to each other at the same distance. One was bright, one was dim. Not all stars are the same. The other thing Mitchell pointed out, which is quite interesting, is he contemplated what would happen if you took light coming from a star and made the star more and more massive and kept going as far as you could go. What would happen? Could gravity affect light and keep it from getting out from the star, which is basically a black hole? So he and the French scientist Laplace were contemplating black holes in the 1700s. Rather amazing. Okay, now we come to probably the most interesting part of this history. It's about Joseph Fraunhofer. He has quite an amazing story. So he was born into a family of about 12 children. His father was a glazier, and a very poor family. There was no chance for any education in this family. And his mother died when he was about 10 years old, and his father died when he was 11 years old. So he and all his brothers and sisters were orphaned. And he grew up near Munich. And so the town tried to match him up with some other family that would take him in. And there was a mirror maker, and since Fraunhofer grew up in a family that glazed glass, made windows, they figured he might know something about glass. And so he was basically apprenticed at age 11 to a mirror maker in Munich. Now, as an apprentice, he was supposed to get time off to go to school on Saturdays, which the mirror maker did not allow him to do. Made him work. And so he had no education at all but at that point. Then, a couple of years later, the building that the mirror maker was working in collapsed, a 4-story building, and he was on the bottom floor. The mirror maker's wife was killed in the collapse, but Fraunhofer wasn't. He was near some shipping crates that held up the beams as they fell down, and so he had a little cubby hole to hide in as this building collapsed around him. And so the people in Munich heard him crying for help. Munich's Prince Maximilian Joseph and a businessman friend of his came down to oversee the relief efforts. And they finally, after hours, were able to pull Fraunhofer out. And this changed his life entirely because the prince took an interest in him, gave him some books, and finally gave him enough money to buy himself out of his contract with the mirror maker. Had that not happened, we may never heard of Joseph Fraunhofer. He went on to become the world's best optician. He made the world's best telescopes by far, apparently quite exquisite telescopes, both visually and in function. And he then put a prism in front of the light coming out of the eyepiece of the telescope and discovered what are now called Fraunhofer lines in the solar spectrum. So he's basically the father of what we now call stellar spectroscopy. Quite an amazing person. He built his last two telescopes that he built went to two people. One named von Struve, who I'll show you in a minute, and the second to Bessel, which I will also show you. Both of those astronomers wanted to measure stellar parallax, of course. He died, by the way, at age 39, probably of tuberculosis or something like that, very young. So let's go on to Friedrich Georg Wilhelm von Struve, here, pictured here. So he used Fraunhofer's 9.5-inch refractor, which was a very big telescope at that time. And he had a micrometer eyepiece. That is, in the eyepiece, he had little crosshairs. And he could actually turn a dial and move the crosshairs in order to measure positions very accurately. And he measured the position of Vega, one of the very bright nearby stars, relative to a background star, as Galileo had suggested. And in 1836, he told Bessel and others that he thought he had a possible detection of stellar parallax, and that the parallax of Vega, the shift in angle over 6 months, was about 1/8 of 1 arc second. But he didn't have good enough data. In fact, I can show you if you can see this. This came out rather light. He didn't think he had enough data to convince people that he'd measure a stellar parallax, and that's because over the centuries there had been many, many claims of stellar parallax that all turned out to be wrong. I just haven't shown you any of these. So here's his data points averaged up a bit. So in 1836, end of 1835, he measured a point here. This is angular shift in degrees as a function of time over a few years. He has 1 point here, a point here, a point here, and a point here. This time span is 1 year, and these points are separated by a few tenths of an arc second. So while this wasn't good enough, although today people would accept this as a probable detection, he didn't claim it to be. Friedrich Wilhelm Bessel heard about von Struve's parallax attempt, and he had been wanting to measure parallax for a long time. And he had gotten Fraunhofer's last telescope, which was basically, it's called a heliometer design. And what they did is they took, after Fraunhofer made this beautiful lens, they took the lens and he had it cut in half. And so you'd have two hemispheres of this lens, two pieces, that you could mount and slide, one with respect to the other. And the advantage of this for this measurement was that if you look at stars, they twinkle. Basically, they're jumping around a little bit on the sky. And that's really limits your accuracy to which you can make position measurements. But if you have two nearby stars, they're going to jiggle around together. And so by sliding one lens with respect to the other, one half of the lens with respect to the other, you can align the two stars on images on top of each other, and they'll both jump around together, but you can make that alignment very accurately. And so he was able to measure the first believable parallax in 1838 of a star named 61 Cygni. And I can show you his data here. So he had the star 61 Cygni measured against two different background stars at different positional offsets from the star 61 Cygni. So he measured 61 Cygni versus star A, background star. Let me come over here. And he has a lot of measurements. He basically observed it every night he could for 1 year, since he realized that von Struve was very close to getting a parallax. And that's quite a convincing detection of the line through there is what you would get from parallax from the Earth's orbit. Using star B, he got a similar result. Since it's at a different offset in angle from 61 Cygni, you get a different effect. And so that's the effect you would expect for this parallax of 61 Cygni for that background star. I've taken this data and reanalyzed it, and I get these two numbers for parallax. 0.37 degrees, about a little over a third of a degree, with about 10% uncertainty for star A. And for the reference star B, you get a smaller value, about a quarter of an arc second, with also roughly 10% uncertainty. So he just averaged these two results, 0.37 and 0.25, and he reported a parallax of 0.31 arc seconds in 1838. This was enough to convince people that he'd actually measured the first distance to a star, and he basically gets the credit for that. This is the actual value measured these days with an accuracy of about 1/1000th of a second of arc. So you can see he did have about a 10% measurement of the distance to this star. So let's go back to Struve for a minute. Remember, he announced a tentative or plausible detection of Vega with a parallax of 1/8 of an arc second. He was observing through that next year and beyond. And once Bessel, of course, announced his result, he had to quickly analyze the rest of his data. And I showed you the 4 data points here, this one, this one, this one, and this one. He continued to observe and got this. Each year it goes up and down, which is what you expect for parallax as the Earth goes around the sun. But he'd obviously recalibrated his data, because this data gives a parallax or an angular shift of about 1/4 of an arc second, not 1/8 of an arc second. And so he announced the distance to Vega to be 1/4 of an arc second, and it's probably because of that recalibration he didn't get much credit for this, because people said, well, we don't even know if this is right because of the factor of 2 change. And certainly people thought the first measurement in the first year, which wasn't very accurate, probably was wrong. It turns out the parallax of Vega is very close to 1/8 of an arc second. He had it right in the first year. See, do I have the number up there? It's that's the fit of his data, giving 0.26 arc seconds, which is what I measured from his data, which agrees with this. But he obviously recalibrated the data and probably got it wrong from that. Well, after the first parallaxes were measured, measuring parallaxes to other stars went very slowly. And it wasn't really until photographic plates were used in astronomy that it made a big impact. And actually, right here in Charlottesville at Leander McCormick Observatory, there was a major effort using the 26-inch refractor and photographic plates. The director, Samuel Mitchell, at that point decided to dedicate a large amount of telescope time to measuring parallaxes. And between 1914 and 1925, measured 700 parallaxes, all done here in Charlottesville. A major achievement. Well, I'll skip forward now from 1925 through work that was done over the next decades to the end of the 1990s. Very recently, the European Space Agency launched a pair of optical telescopes into space to measure parallax, just purposely for measuring parallax. The project was called Hipparcos, for High Precision Parallax Collecting Satellite, in honor of Hipparchus, the Greek who measured the parallax of the moon. And they measured about 100,000 stars, and the parallax accuracy was about 1/1000th of an arc second. Exceedingly accurate measurements. That gives you a 10% accurate distance for a star that's about 100 parsecs away, or about 300 light years away. And so the Hipparcos mission was able to map all the stars in the greater vicinity of the sun, all the bright ones. Well, let's say you want to now know what the Milky Way looks like. Let's go a grander question. And basically, it's maybe rather surprising, but we really do not know what the Milky Way looks like. The Milky Way is our galaxy. It appears as a bright swath across the sky if you can get to a dark site to see it. Hard to see these days anymore. The problem is it's a disk-like system, and we're inside the disk. And so we can't get a picture like this. You'd have to get into a spaceship, travel at the speed of light for some 5,000 or 10,000 years to get away and look back and take a picture, and then spend the next 10,000 years sending the picture back to the US here. So that's not going to happen. We think that the Milky Way might look like a cross between these two external galaxies. So this galaxy has two nice big spiral arms, and it's got a big giant, what we call a bar, in the center of this galaxy. This galaxy over here has roughly 4 of these spiral arms and a much smaller bar, if there is a bar in there at all. Probably if you blended these two together in some way, you'd get something that looks like the Milky Way. Now, there is a successor mission to Hipparcos, which is called Gaia. The Europeans are building and going to launch this next year. And it is hoping to measure parallax angles down to 20 micro arc seconds, or 0.00002 arc seconds. Very, very small angles. That would allow you to map a portion of the galaxy that looks like that. Here's the range that Hipparcos did. So the Hipparcos satellite, which got 1,000th of 1 arc second accuracy, could map stars in about that small circle. But you need to do a lot better if you're trying to measure distances across the Milky Way. So, what do you need to do this? What's the best instrument? And the best instrument is very long baseline interferometry. It's a radio technique where you take telescopes and you can spread them across the Earth. This is the schematic drawing of the very long baseline array that NRAO runs. It has 10 radio telescopes from St. Croix in the Virgin Islands to Mauna Kea in Hawaii to New Hampshire, and a lot of telescopes around the western states. The advantage of this sort of a telescope system over an optical telescope, even in space, there are 2 real advantages. One is that radio waves are not bothered by dust. The Milky Way is full of dust, and at optical wavelengths, you can't see very far through the plane of the Milky Way. So even when you think you're looking toward the center of the Milky Way by going out at the night sky, you're not seeing very far through the galaxy, maybe about 20% only. So if you want to see the whole galaxy, you have to do either at radio waves or possibly at infrared waves. The second great advantage is having a telescope that is spread across the Earth, which gives you very high angular resolution intrinsically. Basically, with a telescope like this, it would be like having your eyes able to see radio waves and have your eyes separated by the size of the Earth. It gives you an incredible angular resolution. And the parallax accuracy one can get is about 5 micro arc seconds, which is this number up here. 5 zeros and a 5. Now, if your eyes could see a bright source, for example, if you took a snail and you strapped a very bright source, a laser source, on its back, put the snail on the moon, if you could measure that angular shift, you could see the snail move in about 10 seconds. So it's really a very small angular shift, 5 microarc seconds. It's how far a snail moves in about 10 seconds on the moon as seen from us here on the Earth. Well, what are we aiming to see? We're aiming to map the Milky Way, and this is an artist's conception of the Milky Way. It's a fairly educated artist's conception. The artist is an astronomer and used a lot of information that we've generated and others to try to come up with what the Milky Way might look like. But what we want to do is actually determine what all the spiral arms look like, where they are, how many there are, by directly measuring objects across the Milky Way. So let's focus for the moment on the upper right quadrant of this artist's conception, and I'll show you basically the results we have to date. Now these are results that come from 3 arrays of radio telescopes that do very long baseline interferometry. I've shown you the very long baseline array. There's also an array in Japan that is actually dedicated to measuring parallaxes called VERA, and they've made a lot of parallax measurements. And there's a third array in Europe called the European VLBI Network, and they have actually measured about a handful of parallaxes so far. So combining all the results from the VLBA with those published, a lot of them published by the VERA array and a few from the EVN, we can make a picture of the Milky Way that's indicated here. So the background is this artist's conception again, which is, to some degree probably right, but probably wrong in many details. And so this is a map, a plan view. Here's the center of the Milky Way. The sun is here. It's about 8,000 parsecs, or about 32,000 light years between here and here. A long way. So you'd have to travel at the speed of light for over 30,000 years to travel from the sun to the galactic center. It's thought to have an outer spiral arm here, and we've measured between the VLBA and the VERA results about 5 sources in the outer arm. I've got 3 I can see from here and probably 2 hidden. So between these 2 arrays, we're starting to trace out the outer arm in the Milky Way. We have a lot of sources of what's called the Perseus spiral arm, all these purple ones here. And we also have a couple over on this side. Here's one that tacks down the Perseus arm very distant from us over here. One surprise is what's called the local arm, shown in yellow. These are all now massive regions where stars are forming, where we've measured the distance directly with parallax. It was thought that the local arm was sort of a little unimportant entity in the Milky Way. Astronomers often called it a spur, which means a little piece that comes off a spiral arm. But it really seems to be a major component of the spiral structure of the Milky Way. So we're finding that out. As you go inward from the sun, the first arm inward is called the Sagittarius Carina arm, shown in green here. And we have a fair number of sources between all these arrays that are along that arm. As one gets close to the center of the Milky Way, it gets much more confusing, and we're going to need a lot more observations to get this. There's thought to be a spiral arm called the Scutum Centaurus arm, which is shown with the sources in red here, and maybe some other arms that are very close to what's called the bar in the Milky Way, right here. So basically, these major programs now are directly mapping the Milky Way. And in the next few years, we should be able to trace out these spiral arms in much, much better detail and really be able to make a picture of what the Milky Way should look like that's based on solid scientific evidence. Well, so far I've talked about measuring distance only. Very interesting to astronomers is measurement of motion. If you measure motions, you can measure masses because most motions in astronomy come from gravity. And so, for example, if you took the solar system, took the Earth going around the sun, if you knew the speed that the Earth is going around the sun, you could calculate the mass of the sun from Newton's laws. However, if the sun were, say, twice as massive as it is, we would be going, if the sun were 4 times as massive, we would be going twice as fast around the sun. So just measuring the orbital velocity of something directly indicates the mass of the central object or the mass enclosed. So can we use our observations here to measure essentially the mass of the Milky Way and by how fast it spins? So for every point here, like that one, we not only know where it is in 3 dimensions because we've measured its coordinates and its distance, we also have measured its motion on the sky. It's called proper motion by astronomers. Knowing its distance, we can turn the angular motion we measure into a linear motion in, shall we say, miles per hour. And we also measure what are called Doppler shifts of lines, which tell us the motion along the line of sight. So we've measured the full 3-dimensional motion of every object up there. And that allows you to calculate essentially how fast the Milky Way spins. So here's a plot of rotation speeds So velocity of rotation going vertically here from 250 kilometers per second, which would be about, what, 150 miles per second, down to 100 kilometers per second down here, as a function of how far you are from the center of the galaxy. This is 5,000 parsecs, 10,000 parsecs, 15,000 parsecs. Now, we're able to do this very easily for an external galaxy. And our nearest neighbor in what's called the local group of galaxies is the Andromeda Nebula, the Andromeda Galaxy. M31, it's also called. So we're standing back from it. We can take pictures with telescopes. We can measure Doppler shifts and therefore measure how fast it's spinning directly. And so these red points give you measurements of how fast the Andromeda Galaxy is spinning as a function of distance from its center. And basically, you can approximate all those red points as almost by a horizontal line with a rotation speed of about 250 kilometers per second. Now, from the measurements of parallax and proper motion of all the stars, the young stars that I've been talking about, we can basically say that the Milky Way is going at almost the same speed, is rotating at almost the same speed, something like that, between about 3,000 parsecs to about 12 or 13,000 parsecs from the center of the Milky Way. So basically, astronomers call these rotation curves, and the rotation curves are basically very similar for the Milky Way and Andromeda, or so it looks to our data. It's a very controversial result. Astronomers had previously thought that the rotation speed of the Milky Way was 220 kilometers per second. So those blue lines should have been moved down to about here. And that the Milky Way rotated quite a bit more slowly than the Andromeda Galaxy. And since rotation speed in astronomy is typically from gravity, as I mentioned, it would mean that the Milky Way galaxy was much less massive than the Andromeda Galaxy. It now looks like they're about equal mass or comparable mass. So, for the first time, we are now measuring the structure of the Milky Way and its rotation. And this is the picture that people would have put up a few years ago for the Andromeda Galaxy and its little cousin or little sister, the Milky Way. But it now looks like this is a better picture. The Milky Way is probably comparable to Andromeda. Now, they're not identical twins. They certainly are going to look different. We know that. But basically, we shouldn't consider the Milky Way the little sister of Andromeda anymore. They're much more like fraternal twins. Well, when we announced this result a few years ago, at an American Astronomical Society meeting in a press release, it was actually picked up by the press quite a bit and made all the major newspapers and the New York Times. And from that, it was picked up by the Colbert Report. And I'll show you this skit.
Yet another edition of our long-running Newbery Award-winning series, Little Victories. One of my favorite pastimes is lying back in a field, staring up at the stars. Looking into the vast, limitless expanses of space makes me take stock and realize just how truly significant I am. I mean, the stars are so small. My hand can cover like 1,000 of them. Giant balls of burning gas. I'm not buying it. But there's one thing that always bothered me about space is that the Milky Way, America's galaxy, was significantly smaller than our intergalactic neighbor, the Andromeda Galaxy. Yes, it's okay to boo. They hate the Andromeda Galaxy. So we're always overcompensating by going around bragging about how big our dipper is. But folks, I've got some good news. Astronomers measuring the rate of spin of the Milky Way galaxy have calculated that our galaxy has 50% more mass than previously thought. That means, we are not smaller than Andromeda, we're about the same size. In your face, Andromeda, bang! Like that big bang! You're so tiny, I've seen nebulas with bigger H2 regions. We have a black hole in the center of our galaxy, and you're an ass. your apparent losertude is a perfect 10. Ah. How's that feel, Andromeda? That's really going to burn when those insults reach you in 2.5 million years. I await your response. We'll be right back.
Okay, that's it. I'm not going to top that. So if you want, I could answer questions, if you have any. There we go.
Are you able to identify any non-circular motions possibly induced by spiral?
Okay, the question is, are we able to see stars that aren't going in perfect circles around the sun? And indeed, they don't. Yes, we're able to identify those very accurately. Now, do they come from gravitational effects from having spiral structure in the Milky Way? Probably to some degree, and that we're working on that. We really don't know the answer.
Other questions? Too good a job.
Too
All right,
clear.
well, once again, let's thank Mark again.